was quietly nervous, worrying about the forecast for this morning, thinking, okay, I'll pack my bag last night. And then when I looked at the weather for today, I thought, Melbourne, what are you doing? And then I realized when I looked out into the size of this hall, I thought, well, if this lecture theatre didn't have a heat problem before, it's going to have one very shortly. I'm going to turn myself down because I'm using my teacher voice and it's ruining this microphone. Let's put that back down to something reasonable. Can you still hear me at the back? No, too far. Okay, that's fine. How's that? Happy medium? Yes? Okay. So we're talking today about, well, we're talking yesterday and today about teachers creating impact. And when I thought about that theme, I wanted to address it, well, hopefully from a bit of an angle that maybe we as mathematics teachers don't often think about, which is, we have that classical question of students saying, Sir, Miss, when am I ever going to use this in my real life? And this is kind of the classic question that gets given to us. And over 10, 11 years of what I feel like I've come up with lots of good answers to that question, I realized that whenever I focused on outward effects, you can get this kind of job. This is the kind of problem you're going to encounter out in the real world that these practical skills will help you with. I found that these students were not satisfied by such answers, even when I thought they were pretty good answers. And I came to realize that the questions that they were giving me, and I wonder if you've had this experience before, this realization, that question was not a question. I think the way Dan Meyer says it's really helpful. It's not a concern for the future that these students are expressing. It's a complaint about the present. It's that this class sucks. Why should I have to put time and effort into something I'm not enjoying and I don't see the purpose of? And so rather than focusing on outward effects, that's why I've titled today's session, Mathematical Dispositions, which we'll come to shortly, Teaching for Inner Impact. Now, to explain why that title is what it is, I need to begin by asking you a bit of a question, because Michaela gave me that very warm introduction. Thank you, Michaela. So you know a bit about me now, but I know almost nothing about you. So for that reason, I have a question for you. And I'm going to ask you to discuss it over the next couple of minutes with the people around you. It's the question, why do we even teach this subject? And I don't mean, yes, it's because the Department of Education, because our curriculum body says we have to, because there's so many exams. I mean, why that? Why do we make mathematics a compulsory subject for so much of a student's career? Many things are not, many things which are really important and valuable. Why do we even teach it? If that's a bit too esoteric and philosophical for you, let me just give you a second option. In the Australian curriculum, we focus on very specific parts of mathematics. There is a universe of mathematics out there, which we decide over the course of 13 years. We just don't have time to look at all of it. So then my question to you is, why algebra? Why trigonometry? Why calculus? Why matrices? Why this mathematics? What is it that has led us to this choice? Do you have an answer for that? I'm obviously not expecting that there are people in this room who were part of the decision-making process for that. But now we're part of it. We've bought into it as classroom teachers every day. We need answers to these questions. So I'm going to give you a minute or two just to discuss this with the people around you, and then we'll come back with your thoughts. Have a think, have a chat. I'll talk to you in a minute. All right, I'm really sorry to give you such a short amount of time. But put your hand up if you can see and hear me. Put your hand up if you can see and hear me. Put your hand up if you can see and hear me. See, teachers, we're the worst, aren't we? Thank you, hands down. Okay, so I wonder if anyone is brave enough, thoughtful enough. I don't want like a really detailed answer. I just want your knee-jerk response, really. And I got a few down here in the front row. Anyone want to be, yeah, please, that's enough.
This is my colleague's idea.
Tried and true method, volunteer someone else's thoughts. Thumbs up.
So it's like chess and like other kinds of reasoning activities where the things that you have to do to work out your maths are the same kinds of thought processes that you actually use in your everyday life when you encounter problems and you've got to do three things and you've got enough time for one, and all these things that we meet every day, that kind of reasoning is what we find in.
And you're looking for patterns and things.
Fantastic. Okay, so we're talking about reasoning, pattern recognition, which are things which we do all day, every day, even if they're not necessarily numerical or mathematical, but that skill is something we learn in mathematics. Fantastic, thank you. Okay, someone want to go a completely different direction? Someone who said something else? Yeah, in the middle.
So our idea was kind of that it becomes a mathematics is a universal language.
we teach a very similar set of maths here in Australia as they do in the UK, the US, and around the world as well.
So this idea of mathematics as a universal language, in fact, one of my favorite quotes is from Galileo, which maybe some of you are familiar with, that mathematics is the language with which God wrote the universe. So it's universal language in a quite literal sense in some ways, okay? Fantastic. Can I get maybe one more? Anyone else who's brave enough? Yeah, down here.
So, the particular choice of mathematics that we teach is largely historic. And in fact, it should be open to question because the world is changing very rapidly and it could well be that some of the selections that we make are not appropriate for us.
When the head of AMT gets up and says, you know, well, actually, I think we should question that. Thank you, Mike. I appreciate that. It's very insightful, actually, and that's why I said, why this mathematics? And I think this is something that, broadly speaking, you know, from a New South Wales background, we are questioning this, and we're reinvestigating it and looking at it as a fresh question. Now, thank you for your thoughts. In a room this large, we could get another 300 different responses, and I think they'd all have something valid in them. I'm not going to be so bold as to say, I have the answer to this. I'm going to point to someone else who's been bold enough to say they have the answer to this. And that, of course, is the Australian Curriculum Assessment and Reporting Authority. Now, I'm out of Sydney, so I have to appeal to something broad enough that we can all agree on. Now, ACARA has this definition, not for mathematics, but for numeracy, which I know we distinguish between, but there are enough points here that I think are relevant, which I bet you touched on in your conversation, that I think it is a helpful touch point to use as our launch pad into the rest of our time today. Now, I'm not going to be silly enough to read all of this wall of text for you. I'm not even going to ask you to do this. Here's what I'd like you to do. I wonder if you can just skim over these 2 paragraphs with me. And don't worry about every word. I just wonder if you pass this for meaning and emphasis. What is it that you think the curriculum writers were particularly trying to convey? We're trying to say, hey, this is really important. This is not just part of the definition which we're just stating for the sake of it. This is actually something instrumental we want to communicate about what mathematics and numeracy are, what we want our students to become, why we teach this subject, why we make it compulsory in our curriculum. There's a whole bunch of things that you could probably pick up on. There are a few words I particularly notice. Here's the first pair. Did they come out to you as well? In my family, I'm the grammar Nazi, which makes me an excellent head teacher to check report comments, but a terrible person at home. Everyone hates when I'm like, actually it's whom, not who. But as a person who is fascinated by grammar, adverbs are really interesting to me. Adverbs, right? These words here, adverbs, are completely superfluous in a sentence. You don't need them. You could take these 2 words out and everything would make perfect sense. It would make perfect sense, but it wouldn't say what it currently says without those 2 words. These words are super important, aren't they? Confidence. We don't just want our students to have knowledge and skill. We want them also to feel about that knowledge and skill a particular way when they are using it. We want them to have confidence. Purpose. I remember being my opinion in something, half of your minds is about to lower dramatically, but I didn't take physics when I was in year 11 and 12, and as a consequence, some people are excited, okay, that's fine. As a consequence, when I got to, for example, d half v squared on dx, I was like, what does that have to do with acceleration? I clearly remember thinking I could work out the purpose for this, but frankly, I do not have the time or emotional space to wrestle with this. I'm just going to learn it far enough so that I can get answers to 85% of questions, and then I'm just going to say, case closed, I've got to move on. Which, of course, is something sad. I look back on that with, disappointment in myself, but I think it's emblematic of what many of our students do. They do not use that mathematical knowledge and skill purposefully. They use it because they've been shown an algorithm and they are faithfully repeating it. And we are emphasizing to them that they are doing the right thing because they get the exact answer at the back of the book. But they're missing purpose. Now, these 2 words are very interesting to me, but there's another pair of words which is even more interesting. It's what I sort of flagged in the title of today. And I know it's important because mathematicians, right? We love few things. I mean, we love a lot of things, but we love few things more than we love brevity and efficiency of communication, right? It's why, who's got time to write? Take the sum of all of the infinitesimally thin rectangles over this interval. Let's just stretch out an S. That'll do, right? We love being efficient in our communication, which is why when you see a word come up not once, but twice, that should indicate to you, oh, this is important. They think it's important enough to emphasize in both of these sentences. Now, dispositions, what are these about? This is me getting back at that idea of teaching for inner impact, right? So often we focus on, can this student use the cosine rule? Can they recognize whether this requires integration by parts or not? We're looking at something outward, right? And we say, okay, well, we have the mathematics proficiencies. We want them to demonstrate understanding and reasoning and problem solving and fluency. And those are kind of a little deeper, but I want to dig further. I want to say, what's underneath that? What's inside a student? That's disposition. That is what mathematics is really about learning. What trigonometry or statistics or algebra is just an avenue. It's just a theater in which to learn those dispositions. I want to talk about 3 today with you. And I'm going to do this in as practical a way as I can. They're dispositions that I think are often disassociated with mathematics, I think. And I think that we and our students and society, as a consequence, suffer by that disassociation. So I want to try and do what we can to ameliorate that today. Collaboration, creativity, openness. If you're the note-taking type, do not fret. We will come back to each of these in turn. Let's begin with the top one, which is, if my clicker wakes up, collaboration. Now, I'm a bit of a film buff. I know there's some people here who enjoy films. And these are 3 of my favorites. And I always struggle. When I show students these pictures, they don't know some of these older movies, which breaks my heart a little bit. But maybe, for a room of this size and age and demographic, you probably know why it is that these are 3 of my favorite movies of all time, right? Because Matt Damon in Good Will Hunting, Russell Crowe in A Beautiful Mind, and Benedict Cumberbatch in The Imitation Game, say that 10 times fast. In each of these 3 movies, the hero, the main character, the protagonist is, say it with me, a mathematician, right? And I think it's great. Thank you, Hollywood, for being willing, at least at some points, to take someone who does maths all day long and make them the hero, make them the protagonist, right? Now, I think that's wonderful. It's part of why I enjoy these movies. But I have a bone to pick with Hollywood in the way that they've portrayed these characters. Because if you've seen any of these movies, and particularly if you've seen all of these movies, you will know that all 3 of the main characters, all 3 of the protagonists in the movie are portrayed characteristically as a loner, as someone who works by themselves, as someone solitary who doesn't have any social skills, probably has poor personal hygiene as well. They don't get along with others, right? Now, sadly, I think our culture and even our profession have bought into this lie. I mean, I admit, partly for historical reasons. I mean, Alan Turing, who Benedict Cumberbatch portrays in The Imitation Game, had in many, many ways, a really tragic story. If you don't know anything about it, you should go and find out about him, or just watch the movie. So there are some historical reasons why we see that, but there are also non-historical reasons. Matt Damon's character is completely fictitious, right? And yet, the stereotype, right, the caricature of a mathematician is someone who works alone. And this is not true. This is a disposition that I think we are mistakenly feeding into. Now, to their credit, Hollywood's getting slowly better at this, slowly. If you haven't watched Hidden Figures, that's about the amazing team of African-American women who pretty much did all of the maths to get human beings into space with NASA. Really amazing story. And The Man Who Knew Infinity is about the Indian mathematician Ramanujan and his partnership, his collaboration with G.H. Hardy. It's literally the stuff of legends. So I think we are slowly getting better as a culture at recognizing the collaboration at the heart of mathematics, but I don't think we're still all the way there. Because this is nice in Hollywood, but what does it actually look like in our schools? Well, let me give you 2 illustrations for what it might look like in our schools. The school I teach at in Sydney is called Cherrybrook Technology High School. We're a large school. We have 2,000 students from Year 7 to Year 12. We're a comprehensive public high school, so everyone in the region just comes on in, and we've got all this medium density stuff increasing around us. So 2,000 kids is kind of what we sit at, and we fluctuate up and down year on year. These kids are in my classroom at lunchtime, not just because we have a lot of kids and not much space. It's because on Tuesdays and Fridays, Year 11 students, those ones in the smart red ties there and there and there, if you can just make it out, these Year 11 students volunteer their time as peer mentors, peer tutors, to these Year 7 and 8 students who come in needing help with homework, struggling, having had very, very diverse experiences, as you can imagine, from our roughly 13 or 14 feeder primary schools. And they all come in, and we give them a peer support program because we know socially they need support coming from all these different places to find their feet in the school. And yet academically, for some reason, we play by different rules. We say, you work it out, we're going to give you all 30 of you exactly the same experience for the rest of the year, and you should be fine. Well, I thought they're not fine. So, things in the Department of Education aren't complete without a corny acronym, so I started calling this 4 years ago, Maths Pass, peer-assisted study sessions. And students voluntarily come 1 lunchtime, 2 lunchtimes a week to offer their time. Now, you can guess, the Year 7s and 8s, they obviously get some benefit out of this. They get people who are assisting them with the problems that challenge them most, with people who are accessible and not scary like their maths teacher at the front of the room. But what I love about this, what this demonstrates about collaboration, is it's not just the Year 7s and 8s who benefit. The Year 11s, the people who are doing the explanation, and I can even see the nods in the room now because we've experienced it ourselves, haven't we? By going through the act of explaining, they learn. I think it was Einstein who said, you do not understand something truly until you can explain it simply. And these kids, these Year 11 Mathematics Extension 1 kids who think they're pretty hot, they know how to do long division, Year 7. And then they realize they do not understand anything about long division. They know how to do it, but as we know, that's quite different to understanding why it actually works. So this collaboration between mathematicians, I think, is wonderfully important. It's something to unlock for our students. But it's also important, not just between mathematicians, but between those of us in the mathematics space and those of our colleagues and others who are outside it. Let me tell you a story that illustrates that. I mentioned before that my school is very large, 2,000 students, which means there's a lot of teachers, 135 of us, which is why our staff room is so large. Now, this is a combined staff room, and what I love about it is not its size, but its diversity. It's combined between science over here in the bottom left-hand corner, technology and applied sciences in this spot over here near the windows is creative and performing arts. And then lastly, in the top right-hand corner, in the dark where we belong, is the mathematicians. Now, I mentioned before that Kappa, creative and performing arts, sits right beside mathematics. And one day this is I think maybe 3 years ago, I was sitting at my desk trying to write my Year 7 half-yearly reports, which is to say, I was looking for any distraction I possibly could. And I overheard this conversation happening on the other side of the aisle. Now you can see, for example, on this desk that's closest to us, you can see there's shelving that's quite high. So when you're seated at your desk, you can't see who's on the opposite side, but I recognize these teachers by their voices. So I knew that they were visual arts teachers. And these visual arts teachers were talking and chatting amongst themselves, and I was a little confused by their conversation because I could have sworn they were using all these mathematical words as they talked. And I thought, what's going on here? What are they talking about? I tried my best to ignore it. These report comments are not going to write themselves. I tried to focus, but after 2 or 3 minutes of this continuing, I thought, right, I've had enough, okay? I'm going to get up there, turn around, and I'm going to set these visual arts teachers straight. I bet they don't even know what these words mean. Where do they get off using these words that belong to me? And as I cornered the table on their desks, I saw this. Now, you can probably guess some of the mathematical words they were using as they discussed this Middle Eastern tiling pattern that they were about to teach to their Year 8 class that afternoon, right? Words, of course, like symmetry and polygons and tessellation and on and on and on, right? And in a flash, I realized I'd been wrong, very wrong, in at least 2 ways. Number one, these words, these concepts, these ideas, they did not belong to me. They do not belong to us. Mathematics is something which is a universal language. It belongs to everyone, even those who don't think it belongs to them. That was the first way I'd been wrong, claiming that ownership. But secondly, I'd been wrong to think I'm the head of mathematics in the school. What does anyone else in the school have to teach me about mathematics? Answer, a lot. 3 years ago, I'd never seen a Middle Eastern tiling pattern like this before, and my mind just exploded the second I laid my eyes on it. I thought, what else do I have to learn from my colleagues in economics and TAS and science and English? What other kinds of things have I been closing myself off from because I haven't been willing to collaborate outside of my little mathematical world? So collaboration, I think, is wonderfully important. And I want to play a game with you that I think aptly illustrates this. Now, some of you may have played this game before, in which case, I hope you do very well. I expect you to do very well. But for the rest of you, the reason why you had a slip of paper on your chair when you came in or nearby is because I wasn't going to be sure that everyone brought something to write on with them. So if you have something nearby that you can write on, either your own pad of paper that you brought or that piece of paper, I'd like you to get it out. Now, this game is a competitive game. So you're going to need to pair up with someone beside you or behind you or in front of you. Can you pair up, please? And once you've done that, furthermore, I'd like you to elect someone to be player 1 and someone to be player 2. Just scissors, paper, rock. Choose someone. Player 1, player 2. And once you've done so, player 1, could you raise your hand for me? Player 1? I'll know you're ready when half the room has its hands up. Player 1, put your hand up. Wait, who's player 1? Who's two people next to each other. Okay, good. Player 1, thank you, hands down. Okay, player 1, you're going to begin with the paper or the pen. Or the book, whatever you're writing on. Okay. Player 1, you're going to have the first move, and the move is very simple. Okay. What I'd like you to do is I'd like you to think of a whole number between 1 and 4, inclusive. A whole number between 1 and 4, inclusive. So you can select 1, or 2, or 3, or 4. It's not a secret. Just write it down and then hand it to your friend. Okay? 1, 2, 3, or 4, and then player 2, you've got the paper now. Okay, player 2, you're going to do something very similar with a slight twist. I also want you to think of a number 1, 2, 3, or 4, but I don't want you to just write down your number. I would like you please to add your number to your friend. So if your friend just wrote down 2 and you are thinking of 3, then I would like you to write down 5. I want you to write down the sum, okay? Or if you're thinking of 1, you'd write down 3, whatever, okay? We're just keeping track of the totals. That's all we're doing, okay? Player 2, that was your move. Now you can hand the paper or the book back. Now, the battle lines are drawn. This is the way the game works, okay? Player 1, you're going to do much the same thing. If my clicker wakes up, there we go. Whoops, spoilers. Player 1, you're also going to select another number and add it on. You can choose a different number entirely, or if you really want to psych out your friend, you can just choose the same number again. It's totally up to you, okay? Add it on, you're keeping track of the total, hand it back. Now, this is the way the game ensues, but you don't know the most important rule, the rule that will help you win, right? This game is called the game of 23. And the reason why it's given that name is because the person who wins is the person who writes down the number 23. They're the winner. Okay? Now, I'm going to give you about 2 or 3 minutes to play this game. What I want you to do is to play more than one game. Play several rounds. Swap who's player 1 and 2, and see if you can work out a winning strategy. Good luck. Off you go. All right. I apologize for stopping you so soon. We will come back to this idea of playfulness later on, I promise. But you have played enough now that you've worked out or you've experienced what it is that I wanted you to experience. And to test that out, I'm going to ask you a question. One of the things I love about this game is that in front of you, you have a running record of every game that you played. At least one game, perhaps 2 or 3 or 4 if you're very good or really terrible at this game. And I want you to look at that record, and I'm going to ask you a question that requires you to have a look at it. Okay? Here's the question. I wonder if at any point, could you raise your hand, in fact, if at any point did your friend, not you, the person you're playing with, did your friend ever write down the number 18? Did this happen to anyone? Yeah? Okay, all right, thank you, hands down. Not everyone, but a lot of you, okay? Now, if that happened to you, I'm going to make a prediction, right? I predict that your friend wrote down the number 18, and then they slid the paper over to you, and you picked up your pen to write the next number, and then you paused. And then you said, I don't want to play this game anymore. because you, of course, have worked out that while the game is not finished, the game is over, isn't it, right? Once your friend has said 18, no matter what it is that you say next, they will win. Now, therefore, you've discovered that when I introduced this game to you, sorry, not sorry, I was lying. This is not the game of 23, is it? It's really the game of 18. Now, hold on a second. Engage your mind for a moment here, because if the cogs are turning, you'll now realize that if we, for example, rewound the clock like 3 minutes, and I reintroduced this game to you and I said, okay, everyone, I usually call this the game of 23, but I'm going to be transparent with you. I'm going to call it what it is, the game of 18, and then I explained the rules just like I did before, and then said play. Maybe you've worked out that if I did that, I would still be lying to you, because it would not be the game of 18. In fact, it would not even be the game of 13, nor is it the game of 8. This is, in fact, the game of 3, which you might have noticed is something that player 1 can say right out the gate, and if they know what they're doing, they can assure victory right out the gate from the first move. So if you were player 1 and you still lost, congratulations, that's like a proper achievement, well done. Now, what have you just discovered? Well, you have now discerned a pattern. By the way, when I play this with stage 1 kids, right? I tend not to give this as the game of 23. I tend to introduce it as the game of 100. And I get them to, I say not between 1 and 4, I say between 1 and 10. Now it might seem like, well, those are bigger numbers, right? But it allows you to re-emphasize friends of 10. And in fact, it makes the pattern, which you've now discerned, much easier to identify because it rounds off to 10s, right? But of course, we could say, let's play the game of n and select a number from A to B and then tell me, what's my winning strategy? Can you determine it for me? What's the first move and the second and the third, right? Now, what's great about this is you've discerned this pattern now and you've got this seed of curiosity that's been planted, but you worked it out by collaboration, right? I suppose you could play this game by yourself. It would be a bit sad. But you didn't even know. I mean, I didn't just lie in the name of the game and say it's the game of 23. I also lied because I told you this was a competitive game. It is not a competitive game because you thought your goal was to win the game. My goal was to help you discern this pattern and become curious about why it is there. And to do that, you were not competing, you were collaborating. You see, collaboration, I think, is at the heart of so much mathematical understanding, admittedly not all of it, but huge parts of it that we miss if we do not cultivate this disposition of collaboration. So that's the first disposition that I want to talk about. But before I leave on and move on to the next one, I just wanted to leave this little postscript. How many of you have heard this phrase before? The strength of weak ties. Anyone? 1? Really? Interesting. Okay. Or 2 maybe. Okay, so that's really fascinating to me because this is the title of a paper from which a phrase which I'm sure you've heard comes from, which is 6 degrees of separation. Now, you've heard that phrase before, I'm almost certain, or maybe you've heard of its Hollywood equivalent, 6 degrees of Kevin Bacon. Great game to play, okay? Now, this paper is talking about networks of relationships, social relationships. And the strength of weak ties refers to this idea. We all have many strong ties, people with whom we're very closely connected, people like our family, our colleagues, people at our school, our neighbors. These strong ties are people who we are closely located to and we spend lots of time with. So unsurprisingly, we form we get a lot out of these strong ties. In fact, we start to speak the same. This is how we gain accents. We start to think the same, sometimes in good ways, having unity, sometimes in bad ways, if you think about groupthink and the problems that come out of that. But these strong ties, obviously, they have a strong impact on us. I think someone said once, you are the average of the 5 people you spend the most time around, which I think is an overstatement, but it still gets at something true, right? Strong ties, obviously important. But weak ties, those ties you have with people who you do not interact with frequently, who perhaps you're very distant from, perhaps you only see them once a year at MAVCon, those weak ties are crucially important because it's by those ties that you get exposed to knowledge and ideas and experiences that you might never experience in your entire life as an individual. Personally, you might never go through that kind of thing. Just like me and my visual arts colleagues. I might have gone for decades without ever having seen one of those designs until they teach it every year. Every year, actually twice a year, every semester they teach that. This is a weak tie. They're not in my team, I hardly interact with them, but I have so much more to gain from them in some ways than I have with those to whom I'm strongly tied. There is a strength to weak ties, and so I just want to emphasize to you the value of collaboration in ways that you might not often expect. Okay, so we talked about collaboration. Does anyone remember what the second one was? It was creativity, thank you. Now, I haven't just chosen creativity because I wanted an excuse to show you this sculpture from the Museum of Math in New York City, even though I totally did use it as an excuse to show you this picture because I think it's just amazing. It's on my bucket list. I've never been there, so I hope to get there one day. But creativity, I think, is something which, as I mentioned in my introduction, is disassociated with our subject of mathematics, and I think that is a huge shame. Now, the reason I think it's a huge shame, or how I started realizing actually we need to bring this back into our subject, is that When I went to university, actually I should back up a second. I'm going to make a confession. Some of you will know this if you know my story, but lots of you will not. I didn't originally intend to become a mathematics teacher. I actually intended, when I turned up at Sydney University, to become an English and history teacher because I love those subjects and I still do. But then I found out about the critical shortage of mathematics teachers and I thought, I want to get a job. So then I dove down into this rabbit hole. But as a consequence, my experience of mathematics at school was, I don't think there's any exaggeration to say, it was fairly ordinary. I certainly didn't enjoy it particularly, and I had not much of an appreciation for it. So when I got to university, and in my readings, preparing to become a mathematics teacher, I encountered quotes like these. I was completely perplexed. I read these quotes and I thought, what subject are they talking about? I never felt mathematics described in these terms, and yet there are these people who I think we would all agree kind of should know what mathematics is, and they are completely unashamed in describing mathematics in these terms of creativity. Now this made me think, this made me wonder, why is it that, random citizen off the street whom we ask, do you think maths and creativity, do you think creativity is something important to maths? I think most people would say no, even people within the profession. In the New South Wales Kindy to Year 10 syllabus, the rationale begins. Mathematics is a reasoning and creative activity. And that one word, creative. So much controversy around including it in our syllabus. Now, if that's something which there's a disassociation with, why is it? Why is it that so many people, including myself back at that time, didn't think of maths as a creative subject? And I thought, okay, I think there are a lot of reasons. I think it's complex. But I think one of them, perhaps the chief one, has to be this. How is it that most of us, and many of us still today, learn, not all, but a vast majority of the mathematical content and skills that they learn? What medium do they use? And this is the medium, right? We say, here is a pattern, here is an idea, here is a theorem, here's a piece of knowledge. Now that you recognize it, go forth and multiply, right? Now, that's not a recipe for creativity. That is a recipe for the opposite of creativity, right? It's like in student leadership programs, it's like, we want you to all learn to take initiative and be original by doing exactly what I say, okay? Now, I hasten to add that this is not the textbook's fault. In fact, the person who wrote this textbook and edited it is a good friend of mine. This is not the textbook's fault. This is the textbook being a textbook. The problem is when we treat the textbook as if it were the teacher, which, of course, it was never designed to do. The textbook was designed to be a tool for us as professionals to use our judgment to use. Textbooks, wonderful servants, terrible masters, right? So I don't want to lay the blame at the foot of textbooks, but they have their own share of ownership that I think they have to take on this, right? So how could we summarize this? I think rather than cultivating creativity and emphasizing it among many of the other skills that we want, I think we've kept students really busy following patterns, following. Here's a recipe, here's an algorithm, go for it. Instead of finding patterns on their own and forming patterns around it, exercising their own creativity. Now you saw all those really smart, eminent people who said those quotes before. Does anyone know who said this? Yeah, I'm not surprised because I said it. I just thought I'd put it in a fancy font and hopefully trick you that someone intelligent said it. But hopefully, I don't know if this resonates with you. The way, when I tried to come up with this, I thought this is why I never realized that there was creativity in this, because I thought if I can just be a good handle turner, I'll be a good mathematician, right? And I didn't realize there was much more to it. Now, to illustrate this, I want to show you one of my favorite kinds of puzzles, and I discovered this from a British journalist and mathematician named Alex Bellos. If you've never heard of him before, then please fix that. Alex Bellos, B-E-L-L-O-S, and one of his employees is with the Guardian newspaper, and I think every Monday he publishes a puzzle. And one of the puzzles he published once upon a time, many years ago, was this. Now, I'm not going to try and pronounce the Japanese because I would do a terrible job of it, but it roughly translates, I am told by my Japanese teachers, to area maze. Now, how do you go through an area maze? Let's have a go at one. Would you please, on the piece of paper you've got, draw this pair of rectangles? I'll talk you through it, and you'll have plenty of time to have a look. There's a pair of rectangles, a smaller one atop, a larger one. The bottom one is 42 square centimeters. You've got a few lengths there. And the unknown, that question mark over there, that area of that shaded rectangle, that's the end of the maze. And like all good mazes, the goal is simply to find your way to the end. Now, I wonder if as you start drawing this, as you start constructing it, the wheels start turning in your head and you've started to work out how to get there. Okay? Now, I'm not interested in the number. I'm not interested in the answer. I'm interested in, we were talking about reasoning before, when we were talking about the introduction. I'm interested in the reasoning pathway that you took to get there. So I'm not interested if anyone can shout out the answer. I wonder, is anyone willing to give me a first step toward the answer? Can anyone see something they might do that might be helpful? Yeah.
Calculate the area of the large rectangle by using the time values of 4 and 3.
Okay, fantastic. So this area down here, which is known, I can use that piece of knowledge and combine it with the 4 and the 3, because those being parallel to the actual side here, combine to give me the width of that whole rectangle. Are you okay with that? Right? Now, I can use that along with the area of a rectangle, which is one of the only 2 pieces of knowledge you need to solve any of these area mazes. I can use that fact to then work out what? Where am I going to go from here? Yeah, the height of this larger rectangle, and we're pretty much there now, aren't we? Okay, we use that 6, we go up the top, and then hooray, Bob's your uncle, or whoever is your uncle, which represents the fact that you have the answer. 16, we've arrived at the end of the maze. Are you happy? You see how this worked? Okay. Now, what knowledge did we use to have a go at this puzzle? Well, we used the area of a rectangle, length times breadth, and we also needed to know how to operate with whole numbers. We did some multiplication, some division, some addition, some subtraction. That's it. Okay? Operating with whole numbers, area of a rectangle. I promise that's all you ever need to solve any of these area mazes. So now, I'm going to give you one with a few more teeth. Have a go at this one. I'm not going to hold your hand through this one. I'm going to let you have a play. You're welcome to work on your own or with the person beside you. If you think you have an answer, don't shout it out. Wave me over, and I'll come over and have a look and see if you're on the right track. Good luck. Well, that got you talking, didn't it? Okay, now, I'm rapidly running out of time. So, I want to show you a way of solving this, and I want to try and emphasize to you what the disposition was that I was trying to get at. Do you remember what it was, and why I think this is a wonderful illustration of it? If you resorted to using fractions, that's fine. But how would you do this without? Some of you are thinking, wait a second, that problem we had before, those areas 16, 42, of course you can solve them with whole numbers. They're so nice and composite. And then, Eddie, you have the gall to give us those pair of numbers. 37 and 43, for real? Prime numbers, what jerks. Okay, now, they are prime specifically, yes, thank you, specifically to push on saying, well, if I can't just work out what the width or the height are, is there another way? There are many other ways. In fact, let me show you one of my favorites, okay? This is a problem-solving exercise, and one of the chief issues in problem solving is, where do I even begin? Where do I start? I have all this information. What might be my beginning point? Well, I think that we don't know very much up in this top left-hand corner. This is the area of uncertainty. By contrast, over here, I know lots. Right? I have lots of information given to me, so that's where I'm going to begin. And so while I can't use the 4 and the 6 directly at the moment, I'm going to put in a construction that allows me to. Right? Now, you're going to say, hey, you didn't say I couldn't use constructions. I didn't say you couldn't, right? Now, using this fact, of course, I can work out that smaller rectangle on the right-hand side has an area that's known. And I can use that as a launch pad to work out the area that's left over. What is the area that's left over? It's 19, right? Okay, now at this point, you've made some progress. You know more than you did when you started, but you hit another wall. What will you do with it? How will you scale it? Where else do I know information that I can use? You know a lot of information out of a particular area in the diagram. It's just hard to see because it's not there. I'm talking, of course, about this spot over here in the corner, right? That rectangle there, which wasn't there before, you know everything about that rectangle. You know its width, you know its height, which means you know its area. Are the cogs turning for you yet? This rectangle I've made down here, what's its total area? It's 37, which should make you immensely suspicious. Because there's this other rectangle with an area of 37, but hold on, same area, same width, which of course means they are not just two different rectangles, they're in fact congruent, aren't they? Which gives you the final answer of 6 because they're the same rectangle up and down, okay? Look, Ma, no fractions. Now, what's my point here? What did you lack? You did not lack any knowledge. I'm confident to say, I think you all knew all the pieces of knowledge you needed. What we often lack when we look at puzzles like this, or puzzles like this, get your phone out because I'm not going to give you enough time to draw this. When you look at problems like this, the struggle is with creativity. The creativity is the piece. I give this to year 12 students who they can work out volumes of solids with cross-sections of similar area with all these ridiculous integrals in them, and they can't work out this problem, right? They're very good handle turners in particular regards, but creativity in maths is something that they've not seen needs to be cultivated. Okay, don't worry, I'll give these slides over to the MAV people so you can have this, or just Google area mazes and you'll find them. I need to really hurry up because I've got 6 minutes to talk about the last thing. So let's get on the board. Openness is the last one. Now, this man here, his name is Keith Devlin, and he and I were both co-presenting at the World Science Festival in Brisbane earlier this year. So I got really lucky. I lucked out and got to have breakfast with him. And he's a mathematician who works at Stanford University. And while we were having breakfast, he said something to me which stopped me dead in my tracks, something which completely threw me, which surprised him because this was something very obvious to him. And he was surprised at my surprise. Here is what he said. He said, you know, Eddie, almost none of the problems worth solving in the world today have just one solution. Obviously, he said. But it stopped me in my tracks because I realized, I actually had to write down his quote word for word on the spot so I didn't forget it, that's why we have it here. I realized that if you took this sentence and you said it, if you said the opposite of this sentence, you would almost to a T have described huge swaths of the mathematics curriculum throughout Australia. Maybe if I say its opposite, you'll see what I mean. You know, almost all the problems that our students are required to solve today in high school mathematics, almost all of them have just one solution. The right one. The one at the back of the book, the one in the marking guidelines, the one that I know matches yours so I can give you full marks. Now, there's nothing wrong with closed problems, problems that have just one solution. They can be really, really interesting and insightful. I have no problem with closed problems. But if Keith is right, then if all our students ever experience is closed problems, then we are selling them a false bill of goods for what mathematics is. They don't realize that it solves a whole menagerie of problems that are in fact open. And Keith told me this story to illustrate. This is a brown UPS truck, United Postal Service, and they're the equivalent of Australia Post over in North America. And I have to double check this because in the US they drive on the right-hand side of the road. Okay. The UPS obviously wants to make their trucks go around North America as efficiently as possible, right? And so we could regard this as a closed problem. Just find the shortest path from A to B to C to D, etc., and then send your trucks on those paths. And that would be the most efficient way to send them out so we could deliver everything. That wouldn't be a bad solution. But the mathematicians at UPS, who UPS hired, realized they could view this as an open problem with lots of different kinds of solutions that might be surprising and counterintuitive. And in fact, they found out, it's quite famous, you should go Google if you've never heard of it, that because in the United States they drive on the right-hand side of the road, the UPS worked out that they would save tens of millions of dollars every year if they forced their trucks to only, ever, exclusively turn right. Now, just think about what that means, right? What that means is if you're the driver behind the wheel and you see your destination over there on the left, they're telling you the most efficient way to get there is to not turn left, but to turn right, then turn right again, then turn right a third time to get over in that direction. Very Derek Zoolander way of doing things. That's a bit confusing. I always wonder who's going to get that joke. Anyway, it's fine. Now, how can that be? How can that be the most efficient way to do this? Well, you can see this from at least two perspectives. Number one, let's think about petrol, right? If you're turning left in the US, you're turning across traffic. What are the chances that you're going to be able to turn immediately across traffic upon arrival at your intersection? Answer, not all that high. You're going to have to wait for your green arrow or for a gap in the traffic. So you're sitting there going precious nowhere, continually consuming petrol, right? And of course, to accelerate from a standing start requires a whole lot more petrol. Even if you have to do it slow down and then turn and slow down and turn, it's more efficient on a petrol point of view. But even bigger than that, of course, There is a human being behind that wheel, right? And that human being is going to be fumbling around with the radio, not paying attention, texting their friend. And so there are going to be, inevitably, with all those hundreds and thousands of trucks going around North America every day, there's going to be an accident, right? And just one of those costs, of course, tens of thousands of dollars in lost productivity. And so turning right constantly reduces the chance of that happening, enough that they can save tens of millions of dollars. Amazing, right? Something that comes from regarding this as an open problem. Now, I'm going to close by showing you one of my favorite open problems from maths class, which is, of course, the problem of pentominoes. Now, some of you know about pentominoes, which is great. We all know about dominoes, right? These are two squares joined together. Pentominoes, as the name suggests, does not have two squares, they have 5. You have to be careful with these objects, right? These objects, sometimes they look different, but they're really the same, right? How would you change that first pentomino to turn it into the second? You're reflexively doing it with your hand, right? All you have to do is spin it 90 degrees anti-clockwise, and there you are, okay? This one you can't get to via rotation, but instead you would just flip, and it's the same. But it doesn't take that much imagination to work out, of course, that there are some which are truly unique. There's no way you can transform that guy to get to the other one, okay? Now, this is an open problem that I want to set you. I actually had 2, but I'm going to only have time for this one. I've shown you there are at least 2 pentominoes, 2 different ones. How many do you think there are? I'm going to give you about 45 seconds to see how many you can come with the person sitting next to you. Have a go, see how many you can draw just on the piece of paper you've got. Good luck. Okay, that's really awful. I'd give you 7 at least, 9 more minutes, but I want to make sure you get out to Moyency on time, so I'm going to hit pause on you. I gave you 2 to start with, and so even though that was very short, I feel confident enough to say pretty much everyone should put up their hand if I say, please raise your hand if you came up with, including mine, at least 4. Yeah? Does everyone have their hand up? Keep your hand up. If you got to 5, 6, 7, 8, 9, 10, 11, keep it right up so I can see, 12, 13, 4. How many did you find, sir? I stopped paying attention. I just kept my hand up. Well, that's probably a good thing for you because there are 12. Now, one of the things I love about this is that the second you see them, you think, how did I not come up with that one, right? Big pat on the back. If you got this guy here, I call this one the stairs. And for some, I don't know why. I don't know why it is. But every time I do this with groups, the stairs are one of the very last ones that people discover. I don't know what it is about it that makes it hard to come up with in our brain. Now, this open problem with multiple solutions, right? This open problem I love because it's so accessible, but more because it leads to, this was just the warm-up for the real open task. Okay? Here's the real open task. There are 12 pentominoes, each of which have 5 squares. So therefore, on the screen currently, there are how many squares? 60, right? Now, we mathematicians, we love the number 60, and society loves the number 62. That's why we designed our time system on the number 60, because it is so nicely factorizable, right? 1 times 60, 2 by 30, 3 by 20, 4 by 15, 5 by 12, and 6 by 10. Right? It's a lot of nice factorizations. Now, each of those factorizations I just mentioned, right? For example, 4 times 15. It's a way of describing a rectangular array which has exactly 60 squares, right? 4, 15, you'd get 4 rows and they'd all be there. So the real open problem is, do you think these 12 pentominoes can be arranged to make a nice, neat, rectangular array with no holes in the middle and no bits sticking out the edge? Now, spoilers, and I'll tell you why I'm not going to get you to do this yourself in a second. Spoilers, you totally can. Now, what I love about this is, number 1, this is so eminently satisfying for students when they arrive at a solution. I tend to get them to work in groups of 3 or 4, and one of the reasons I'm not asking you to do it now is because it's not impossible, but it is fiendishly difficult to come up with one of these solutions just by drawing. If you're going to do this with your class, you really need them to cut these things out, move them around, and it's fine, okay? Now, I get them to do it in groups, And number one, it's so satisfying. Like they come to me, fist pumping in the air, and they're so, delighted. And I have to say to them, we had this game once upon a time called Tetris. Now, fun fact, of course, Tetris is not with Pentominoes. Tetris is with Tetrominoes, which have not 5 squares, but 4, right? A lot simpler, there are not 12 of them. But secondly, what I love is that when students find their solution, it takes like 3 or 4 minutes to come up with the first solution. And then another group, about a minute later, will come up with their first solution. And I say, well, you're mathematicians. One of the things that mathematicians do is when you are to solve a problem, if you come at it from 2 different angles, one of the best things, the most beautiful things about our subject is you can solve it 100 different ways, and if you're all correct, you should arrive at the same answer, right? Please, go be mathematicians and check your answers. And it doesn't take any longer than 5 or 10 seconds for these 2 groups of students to come to me, gingerly holding their arrangement of paper, with a confused look on their face, because they say, sir, our answers don't match. Who's right? Is it us or them? And I always get to respond, yes. Because of course, there are many solutions. This is an open problem. And it's almost impossible in a class of 30 for students to have arrived at the exact same solution, particularly if you try the 6 by 10. By the way, don't be too impressed, I just got these pictures off Wikipedia, so you can do the same. Now, fun little fact for you, fun little exercise. If you were one of the people in the room who's like, I know Pentominoes, okay, well, how about hexominoes? Now, there are a lot more hexominoes. That kid in your class who's like, sir, I've finished all my work, miss, I'm done, what else can I do? Right? If you've got a Gauss in your class, then tell them to have got these. And then there are, if I'm doing this right, there are 35 hexominoes. 35 times 6, if I remember my numbers correctly, is 210, which you can also write as a nice, neat rectangular, as a nice, neat rectangular array. Do you think the hexominoes can be arranged in such a way as to make a nice, neat rectangular array? And fascinatingly, at least to me, even though there is such an abundance of solutions for pentominoes, you want to know how many solutions there are for hexominoes? Exactly 0. And it is a wonderfully elegant, very brief proof too, which I will leave as an exercise to the reader, to work out why it is that it's just completely impossible. Really, really nice problem, okay? So, I better close, right? I had one last thing. I characterize these guys as closed problems, right? There's one answer. And then I realized they're not closed at all if you change your perspective. If what your perspective is, if the thing you're really interested in is, how did your student arrive at that solution? If that's the case, then these guys are as open as anything, right? This is a student, a year 8 girl. She showed me this solution. I deliberately did not use algebra to solve this because I want to make sure whenever I meet like primary colleagues, I don't want to bamboozle them with the X's and Y's. But this girl, she thought, why not? I'm going to put some X's and Y's in here because I don't know what those are. And I know I don't want to interact with fractions. So let's see what happens. This rectangle over here, this one which I know lots about, right? I can do width and I can do length. Yeah, are you okay with that? And that gives me this statement. She did this amazing thing, this creative thing. She said, well, now that I've written down that equation, I can just do everything to this equation, forget about it being to do with shapes. I can do everything with this equation I can with other equations. So for example, I'm going to subtract 6 from both sides. When you subtract 6 from both sides, you get this. You see what she's done? 6 from the right-hand side, of course, gives you 37. When you take away 6 from the left-hand side, instead of having x plus 4 of them, you've got x plus 3 of them. Are you with me? Yep. Now, are you suspicious like you were before when you saw that 37 appear and that x plus 3 appear? Where is x plus 3 on that diagram? Answer, it's on the other rectangle, right? Wait a second. Those two equations are saying exactly the same thing, so therefore it stands to reason that y must be 6. Isn't that beautiful? Like this 13-year-old girl, she was freaked out. I just jumped up and down and she said, sir, it's okay. It's just 6, right? I was like, no, you don't understand how beautiful what you've done is, right? When our students unlock creativity in mathematics, it just sets the world alight. So, I better close. 3 dispositions, right? Creativity, sorry, I can come back, there we go. Collaboration, creativity, and openness. Why do they matter? Well, they matter for all the reasons that when we say, what do we want you to be? Why do we teach you mathematics? We want you to be sound reasoners. We want you to be effective communicators. We want you to be flexible problem solvers, and these are the dispositions that will get you there. That's what I think Inner Impact looks like. Thank you. Thank you.
Thank you.
Okay.